Okay, in this video, I'm going to go over some options basically from the lab today. So the lab had us create three nodes or three different names, and that's not normally the way we do things. So I thought I would go through and demonstrate how we could have done it with one reusable pointer variable, which we'll call new node. And this is a way that we tend to do it. It's the way we'll do it going forward. Okay. So, and this is getting us ready for what we're going to cover starting tomorrow if we have class. And that's going to be creating a class, a linked list class that we can use to um, to not have to include all this stuff every time. Okay, that's really what it comes down to. It's a little difficult sometimes. Okay, but for now, we're going to include this struct node. Okay, so this should be the same as the lab, it's same as in the code that you were able to download. And we have an int, which again can be any data type that you want. And we have a pointer to a node. Okay, we have data and next. Okay. And then in this case, we're doing this a little bit differently. We're going to go ahead and create a couple of node star, so node pointers, pointers to nodes, one called head and one called new node. And both of these are going to be set to null pointer. Okay. So these currently are not usable. They don't have, they point to a memory or they point to nothing. They point to null pointer. They don't have any memory associated with them. Okay. So if we want to go ahead and create, so I'm printing out the message on the screen, building the linked list. Okay. And I'm going to create this new node here. Okay. New node is a pointer. So new node is equal to new node. Easy enough. It's new type node. Okay. We're going to dynamically allocate memory for a node. Okay. And we're going to set the data. Again, I'm using the dash greater than or the arrow because it's a pointer. The new node data is equal to 10 and the new node next is equal to the null pointer. So there's nothing there yet. Okay. And we're going to set the head equal to new node. Okay. So if we look at a picture, a text picture of how this works, we have our head, which points to this first node, and the node is in the square brackets, which has a data of 10 and a next of null. Okay. So we can now say new node equal new node again. Okay. This is going to allocate different memory for new node. Okay. So the line up here, the first time, it allocated wherever it's at, a spot in memory. Saying new node is equal to new node again will allocate a different spot in memory. Okay. So now new node points to this new address, and we're going to use the arrows to say the new node data is 20 and the new node next is null pointer. Okay. So this is just creating the node. Once we've created the node, we want to be able to link it up. Okay. So we're going to say that, and we don't want to use a loop yet. So we're going to say, since it's our second element, we're going to say head, which points to our next element. Head next, which is currently null pointer, is now going to be equal to this new node. Okay. So we now have head pointing to the first node with the 10, which points to the second node, which now points to null. Okay. And then for the third node, we're going to do a traversal this time, okay, to insert at the end. So again, I'm new node is equal to new node one more time. That's getting us our third bit of memory that's node shaped, okay? And again, we're going to set the data and the next, okay? But now we want to add at the end. So we're going to set this current pointer equal to the head. And we're going to say as long as the current next does not equal null pointer, then current is equal to current next. Okay. So what this is going to do, this is going to keep moving. It's going to stop. When does current next equal null pointer? When you're at the last node. Okay. So this will move us. In this case, we have a 10 and a 20. Okay. So we're going to start at the head points to the node with 10. That's not, its next is not null pointer. We're going to go to the 20. Its next is null pointer. So at this point, current points to the 20. Okay. In the picture here, it points right here. Okay. So from here, we can set the current next equal to the new node we just created with 30. That'll put 30 right in there. And 30 has its next equal to null pointer. And we've added that. Okay. We can then go through the traversal. So we're going to see out the list contents. Okay. We're going to set a node pointer temp to the head. We could reuse current if we wanted to. Doesn't matter, but we're going to use temp. While temp is not equal to null pointer, just like we did before. Okay. Uh, Again, not temp next. If temp equals null pointer, we're passed into list. So this will go, in our case, it'll start, since it starts at head, it starts at the 10, then it goes to the 20, and then the 30, and then it goes past the 30, then it's at null, and we're done. We don't do anything else. But every time that it's not the null pointer, we're going to print out the temp data, okay? And then we're going to let temp equal temp next. That just moves it to the next one, okay? So 10 the first time, and then 20, and then 30, okay? I put in here my expected output, which is good when you're testing, should be 10, 20, 30, okay? So here's how we can go through and free all of the memory that we have dynamically allocated, okay? Because we don't really know how much memory is there necessarily. I mean, in this case, we do. We just programmed it. We know there's a 10, 20, and 30. But in general, we don't know that. Okay. So what we have to do, basically, we have to save the node that head points to a different pointer. Okay. And then we can move head to the next pointer, head equal head next, and then delete what was there. That's what we're doing here. So as long as the head does not equal to null pointer, which means we've gone all the way to the end, okay, we're empty at that point. So we're done when we're empty. We're going to set up this node star to delete to be equal to head, okay? So this is going to create this node pointer that points to whatever node head points to. It'll be 10 the first time. I'm moving head to the next element, okay? So now it goes to 20. I'm now deleting that to delete. And again, as I said in lab today, even though to delete is a pointer, this will actually not delete the pointer. It will delete the node the pointer points to. Just a quirk of C++. Okay. And then when we're done, we just say the memory is cleaned up. The program's complete. Okay. So this is more or less what the program uh, in lab did, except we're just using the one pointer, the new node pointer, which is what we're going to be more likely to want to do. Okay. So if I want to compile that, do that with the lab3.cpp dash O. I didn't do the wall, but you get the idea. Okay. And you see that's what it does. It builds the list. It's going to go through the memory cleaned up. Okay. And if you want just to kind of track the memory, there was a question in lab from one of the groups. How do we know what it's deleting? Well, we can in the deletion process, just go ahead and print out what we're deleting. Okay. So before I delete it, I can just say cout deleting node, and that will be the to delete dot data, not dot, since it's a pointer, arrow data. Okay, and that should, if I got my syntax correct, yeah, deleting node 10, deleting node 20, and deleting node 30. Okay. So again, someone had said, well, don't we delete from the end back to head? And we can't do that, at least with the singly linked list that we have, right? Because we don't know where the end is. We can certainly keep track of a tail along with a head if we want to do that, but we're not yet. And we also currently have no way to go backwards. We'll get to something called a doubly linked list where you can go both forwards and backwards. There's a next and a previous. And that would work for that, but it doesn't in this case. So we have to delete. Again, we delete by saving the node that head points to, moving head one forward, deleting that node. Okay. I also wanted to show you, again, we haven't had as much time as I would have liked, so we have to kind of improvise here a little bit. Um, Another way that we could have done this program. And I call this iterative, but it's also interactive, I guess whichever one you want to call it. Okay. So this one, again, looks very much like the program we just did, except I'm going to allow user input. Okay. As I mentioned in lab today, if you want that 10 out of 10 points, your program should have user input and it should have meaningful displays at the end. It shouldn't just print a number that has no context. Okay. So this one, the purpose here, the program is going to build a singly linked list. Again, that's all we're doing. We can go only forward, one node at a time, and we're going to use a single reusable pointer variable, the new node, to create them. Okay. The user is going to be prompted to enter the integers, and if they type in a -99, then that means that they're done. Okay. So the first part looks just like we've done before. Okay. I've added here a print list function. Um, just so we've got that. Sometimes we don't know what's in our list really. It's hard to keep track of. So this, when we're sending a linked list to a function, all we need to do is send the node star pointer. Okay, the node pointer is enough, and then we can get there from there. Okay, so that's all I'm sending in. So on this print list, we always have to think about, okay, and we'll get used to this as we go along. What are the cases when we go to print? Well, it could be that there's nothing there. Okay, we don't want to just throw an error. If we tried to dereference a null pointer, we would get a segmentation fault. So in this case, if the head is equal to the null pointer, then we're going to see out that there's an empty list and return, and we're done. Okay. So if not, if we get to this line, it means there's something there. So we're going to use our current node pointer, point it to head. Okay, we're going to put in here, the first thing we're going to put on display is head with the arrow. Okay, then we're going to go through again while the current is not equal to null pointer. We're going to go ahead and see out the bracket, the current data, close bracket. Okay, and then if current next is not equal to null pointer, we're going to go ahead and print this arrow. If it is equal to null pointer, we're still going to keep going, but we're not going to print out that arrow because there's nothing after that. Okay. So then we go to current equal current next to move it forward, come back up here until we get to the null pointer, which means we're done. Okay. So, and then I'm just at the end of that print statement, I'm just printing out an arrow to the null pointer just so we know that we're done. Okay. In our visual. Okay. So then in our main, like we did on the last example, we're going to have our head and our new node both set to node pointers and set to null pointer. Okay. We're then asking the user with the prompt to enter the integers to add to the list and -99 to stop with some new line characters just to make it look nice. Okay. With our insertion loop, okay, we've just got a while true here. We could have put as long as the value is not equal to -99 or whatever. The problem with that, it can be hard once that -99 happens to get out quick. Okay, so we're gonna make it easier on ourselves by just making while true. While true goes on forever until it hits a break. Okay, we ask the user to enter a value up here. They enter the value. If that value is -99, hit a break. What does break do? Break gets us out of the while, drops us all the way to the end of the while, which is down here. It's then going to print out the list. Okay. But let's assume um, that it's not -99. Okay. We're then going to create the new node. The new node is equal to new node. And we're setting the new node data and the new node next. Okay. We got a couple of cases here. Is it an empty list? Okay, if it's an empty list right now, then there's only going to be one thing to do. We set the head equal to the new node and we're done. Okay. If not, so the case two here, it's a non-empty list. Okay. And the only thing we can do in this version is we can insert it at the end. Okay. So we just did that before, where we're going to go through, set up our current pointer. Okay. And while it's not, the current next not equal to null pointer, we're going to move it. That's going to get us at this point. We're at pointing at the last element in our linked list, no matter how big the linked list is. We're then going to set the current next equal to new node, and we're done. Okay. So in either case, we're going to hit the -99 eventually, or in any case, when we hit the -99, we're going to drop down to the print list, which we just looked at. That will go through, print that out. Okay. We could have put the print here, but I did it as a print function instead. It's left this code here. It's code we're no longer using, but because I wanted to look at it later. Okay. So the cleanup, we're going to free whatever allocated memory we have. And we just saw that same idea here. And this is going to work, right? You can copy this and use it every time you need to. We've got while the head's not equal to null pointer, we're going to set this to delete node pointer equal to head. We're going to move head forward, and we're going to delete what's there. We're going to have a memory cleaned up message there. Okay. So if we were to run this one, I think I've already got a executable for that. Okay. So enter values we ever want. I can enter a 23, and I can enter 45 and a 67 and a 22 and an 11 and a negative 34, whatever. When I hit a negative 99, it's now going to print. Okay. And say the memory's cleaned up, the program's complete. So we should be good. Okay. So again, head points to 23. We can check it here, which points to 45, which points to 67, which points to 22, which points to 21, which points to negative 34, which points to the null pointer at the end. Okay. So this is correct. Okay. In one of the breakout groups, they talked about, again, having the question, why would we use this as opposed to an array, dynamic array? And the big differences are dynamic arrays, even with a vector, require contiguous memory, which with either a large data structure or a small memory may be a problem. You may not have enough memory in one big area. Okay. The other thing is, if we wanted to insert something at the beginning here, which that's what we'll be doing in our next homework assignment, we're going to insert front. That's difficult to do in an array without moving everything. Okay. There's no way to change just that first element. We can't add a new cell. Okay. Also, it's difficult in an array to insert in the middle or delete in the middle. Okay. So arrays are best when you can add and delete from the end of the array. Okay. So that's kind of that. So hopefully this will help us out. So again, tomorrow, hopefully we'll have class. If not, we'll try to Zoom no matter what. We'll be able to go through, start implementing this linked list class so we can just include that file and not have to type in the node and all the inserts as individual functions anymore. Okay. So that's where we're headed. So if you have questions after looking at this, make sure that you let me know. Um, Things do not get better if you just hope they go away in this class, right? Everything builds. We're going to be using linked list to implement stacks and queues. So don't just think I'll take the hit on points and just never understand linked list and I'll still make it through the class. Good chance you won't because we're going to keep using the linked lists. Okay. So let me know for sure if there are questions.